Hello. Hello. Am I audible? Hello.
Yeah.
Shall we start? Shall we start? Okay. Thank you very much, Dr. Kanmani Subbu and Dr. Kesavan, for inviting me for this wonderful forum. So, considering me as one of the expert in the field of additive manufacturing. So, as far as the topic which I would like to discuss today is more to do with additive manufacturing of shape memory alloys. Basically, it's a class of smart materials. So, from the career of my research at IIT Indore, from the starting of my career at IIT Indore. So we were more focusing towards shape memory alloys. So there were some kind of limitation.
Dr. Palani, sorry, I got disconnected in between.
Yeah,
no problem.
We understood
no
that case, no problem.
All right,
no
yes.
problem. So we will start. Okay?
All right, please proceed.
Okay. Started.
So this basically, so with respect to shape memory alloy is concerned, it has a potential application towards different functional fields. Okay, so including dampers for machine tools, it can act as a very good sensor, and it also can act as a very good actuators, etc. But there are some drawbacks which are available, so which will be going through it, and we'll discuss how additive manufacturing can be a promising method for developing such kind of shape memory alloy structures. Okay. Now, when we talk about shape memory alloy structures, it comes under the category of smart materials. So smart material, if you try to look into the family of smart material, there are wide varieties of smart material which are available. So why do we call it a smart material? Because it gives a peculiar behavior. So one example of a smart material is a piezoelectric system. Like you might have heard that there are some mats which are available. So when you try to jump on it, you can harvest the energy. So as an extension of these piezoelectric, there are different materials like triboelectric, then shape memory alloy based polymers, etc. So many such materials are there, which behaves in a peculiar way. So as far as in these kind of smart material is concerned, so on an engineering perspective point of view, so if I try to look into it, so I consider it as a material, or I consider it as a system in which I have an input in terms of either in terms of heat or in terms of electric or in terms of magnetic field, and I get a response either in terms of displacement or sometime in terms of EMF, etc. Okay, so this is how I consider the smart material as. So where I consider it as a dynamic system. So in this dynamic system, so if I try to define the system, so these systems are basically categorized based on the type of properties which I need to consider, or based on the type of qualities it can be taken up. Okay, so the major qualities which comes into our mind is, one is an actuation stress and another one is an actuation strain. So with respect to an actuation stress and an actuation strain, you can classify your material at different functionalities. That is where exactly shape memory alloys plays a major role. So because shape memory alloys has a good amount of actuation stress as well as good amount of actuation strain. Now, if I try to look into the fundamental of shape memory alloy, this shape memory alloy, like you have a ice. So when you try to heat the ice, you get a water, and further when you heat it, you get a steam. Okay, so basically there is going to be some kind of phase transformation. Same phase transformation is happening in shape memory alloy, which is leading to make it to respond to heat. Like what happens is, if you see in this video, so there is a strip which is available. When a slight amount of heat is applied to it, it tries to bend. So basically the motivation behind this is basically it tries to switch between the martensite and the austenite phase of the material. So as far as in this austenite phase is concerned, so it is a high temperature phase with a cubic crystal structure. As far as a martensite phase is concerned, it is a low temperature phase with a monoclinic structure. Okay, so like to give you a clarity about this shape memory alloy, let us consider wire. So this wire, it is initially on the martensite phase. Now I am deforming it. It becomes a deformed martensite. When I try to supply a heat, it comes back to an austenite phase, and again it comes back to the martensite phase. Okay, so this is how basically the cycle evolves in the material. So like this is to give you an idea. So basically this video was recorded in our laboratory, where you could see that there is a spring which is available. So this spring is tied to a weight. Now what I'm doing is I'm trying to supplying a heat through electrical biasing. So when it is when the electrical biasing is supplied, so basically it is in the deformed martensite state. When I try to apply a heat to it, so the heat is applied due to the electrical biasing, which through H equals I squared RT, and because of it, the material reaches to the austenite state, and then it comes back to the martensite state. So we are trying to switch between the austenite phase and the martens phase using an electrical actuation. And this is one video where one of our PhD scholars, so he is trying to deform the spring and he is trying to put it inside a hot water. So when we try to put it inside an hot water, it tries to come back to its shape. So you can have a closer view. Where we could see the response of this material is quite good and it comes back to its original shape. So this is what basically the characteristics of the shape memory alloy, where through with respect to heat, you are trying to manipulate your strain and your stress. In addition to this, there is a behavior of these material which we call it as superelasticity. So this superelasticity is something like it has a capability to store energy. So it can be used as a dampers. So these are the two peculiar capability of these shape memory alloys. Now, as far as the shape memory alloy is concerned, so it has wide varieties of material exhibits shape memory alloy. One major or one standard material which comes into our mind is NITA, which we call it as nitinol. Okay, so basically the full form of this nitinol is basically it is called as Naval Ordnance Lab. This was developed in US for an ordnance purpose, so that is why it is coming up in their trademark. So we have an NITA based shape memory alloy structures. There are some copper based shape memory alloy structures which are also available, like Cu, Al, Ni, Cu, Zn, Al, Cu, Al, Mn, etc. So these are the different types of copper based shape memory alloy. Shape memory alloys are also available. Now you may ask me a question: when should I need to go for NITA structures, and when should I need to go for a copper based shape memory alloy structures? So as far as an application perspective point of view, wherever I have an actuation temperature in the range of 90 to 130 degrees Celsius, then I can go for a nickel titanium. Wherever I have an actuation temperature from 230 to 350 degrees Celsius, then I go for copper based shape memory alloy structures. So wherever my requirement lies within this range, I go for copper based shape memory alloy structures. And wherever my requirement lies within this range, I go for a nickel titanium based shape memory alloy structures. To give you a better picture, actually we have a vehicle. So the heat generated from the bonnet will be sufficient enough to actuate an NITA shape memory alloy structure. The heat generated from the exhaust will be sufficient enough to actuate a copper based shape memory alloy structures. Okay. Now, as far as this shape memory alloy structures is concerned, when we try to look into the overall structure of it, so basically when we try to look into the literatures or based on our applications, either these NITA structures are in the form of a bulk or in the form of a thin film. So as far as this bulk structures is concerned, we can fabricate thick bulk structures and we can actuate it and we can arrest the vibration. So this is one option. So another one is with respect to thin film, it has a potential application towards some kind of MEMS based structures, some kind of micro robotic systems, etc. So as far as thin films are concerned, almost the technology is quite good enough where you can do a thin film based fabrication using E-beam evaporator, using a thermal evaporation, or even using a sputtering, etc., where people have attempted in developing NITA shape memory alloy structures. Whereas in the case of bulk, it is quite limited because there are some issues which are available with bulk structures, because as far as NITA bulk structures are concerned, people were more focusing towards developing a powder metallurgical based systems. Basically, it's a kind of a small cylinder kind of structures which we have developed, which they have developed, and they have demonstrated the shape memory effect. In fact, most of the people have demonstrated the super elasticity behavior because of the bulk structures. But as far as the major challenges is concerned, so this was the major challenges when we took shape memory alloy as our research interest. So we found that there were some kind of issues in considering these shape memory alloys for different applications. The one major concern is basically when we started our research, so shape memory alloy production was not available in India. So we need to get from abroad. Even a spring would cost us something around 3,500 rupees. So we need to handle it carefully. Another option is we get the shape memory alloy either in the form of a sheet or in the form of a wire or in the form of a rod. That's it. So in case if I want to make a spherical structure or a cylindrical structure, there were no vendors available to prepare those structures. Okay, so it was not, in fact, it was not commercially viable for us to prepare those structures. Third important aspect with respect to shape memory alloy is like, if you see these shape memory alloy structures, to get such kind of displacement, we need to have a tedious training. So in order to employ this tedious training, so one option would be we can integrate some kind of composite behavior in it, so that when we try to integrate these composite behaviors, we can somehow reduce the tedious training. Otherwise, training cycle itself will last near to around 50 to 60 times. So in order to achieve this austenite or martensite phase, I need to heat it in a furnace near to the austenite region, and then I need to bring back to the martensite region by putting it in a liquid nitrogen environment. This cycle I need to repeat to get a displacement. So it was a bit tough for us to reach to that particular level. Okay, so these are some of the major challenges which we were trying to address it in our research focus. So in that, one major challenge is to develop customized shape memory alloy structures. So in order to develop customized shape memory alloy structures, the only option which is available, or I would say that it's a fruitful option, is to go for an additive manufacturing system. So as far as additive manufacturing system is concerned, so obviously you might have gone through the different lectures by the different experts where people have attempted different types of additive manufacturing. So we also thought of why can't we explore those options to develop such kind of shape memory alloy structures using additive manufacturing. Okay, so in this talk, so basically we will discuss about, one is with respect to laser-based additive manufacturing of shape memory alloy structures. Second, we have developed a wire arc-based additive manufacturing. So this is a kind of system which we have developed in-house, which is of low cost, which we developed it basically to focus on shape memory alloy structures. Third content which I would like to discuss is something like integrating a laser with wire arc to get a thin structures, basically for some particular applications. We explored the possibility and we could observe that there was a potential focus in this particular region. Okay, and the fourth case study which I would like to discuss is something related to micro additive manufacturing. So this is one of the prime focus currently we are moving upon. So this system is completely developed at IIT Indore. So where we have used a concept called laser induced forward transfer for fabricating microstructures. Okay, so any kind of microstructures, any kind of smart materials can be fabricated, which will be going in detail. Okay, so let us come into the first topic, that is laser-based additive manufacturing of shape memory alloy structures. So as far as this laser-based additive manufacturing is concerned, okay, so this we had a motivation for starting this work. So it was Industry 4.0. Basically, as far as Industry 4.0 is concerned, so we all know about the different industry revolutions. So, like with respect to demand and with respect to the availability of the source, different industry revolution came into existence. So, if you start with Industry Revolution 1, where there was an abundant amount of water and heat, so we were more focusing towards the mechanization. Industrial Revolution 2, we were focusing towards mass production, since our demand was towards mass production. And Industry Revolution 3, since there was a quite explosion related to electronic systems, so we were focusing towards mechanical and electronic components. So that is how robotics and mechatronics started coming into the picture, and we started more focusing towards automation. And now, if we talk about Industry 4.0, it is to name that, or it is to focus on how the system is going to be intelligent. So for that, we have abundant amount of internet data with us. So with respect to that data, we are trying to develop the system. So in fact, to expose you to the Industry 4.0 environment, so this is one work which we had collaborated with one of our faculty members at IIT, Dr. B.K. So where he was trying to develop an intelligent system for where there was an old machine was there. So he need to make it intelligent. So basically, so in order to make it intelligent, so we need to incorporate a good amount of sensors and actuators into those systems. So if we try to incorporate these sensors into these systems, so it can pick up the signal and then appropriately, so it can be easily communicated. So basically your data sets will be quite heavy, and from the data sets you can take logical decisions. So that is what the idea of this kind of system. In fact, the main core of this is to develop a cyber twin from this intelligent machine structures. So as far as in this machine is concerned, we need to develop a customized sensors for it. So that is how this shape memory alloy came into the picture. Okay, so any machine tool, if you take, so when you take any system or any drilling machine or any milling machine, before it fails, two important aspects happen. One is a high amount of heat, another one is a vibration. Since our material is more sensitive to heat, so what we thought is we will just fabricate a structure over the quill kind of thing. So this is a quill. So over the quill, we try to deposit our shape memory alloy along the tool holders. And when there is a heat is getting generated, this shape memory alloy holder gets heated up. And we have trained the system in such a way that it will arrest the vibration. So when it tries to arrest the vibration, so you are trying to prolong the failure for a long. In the meantime, there is an infrared camera which is available. So through this infrared camera, we can pick up the signal, and the signal will be efficiently transferred to the concerned shop floor manager, so that he can get involved in maintenance of the equipment, or he can make the necessary decision in changing the process flow. Okay, so here the major challenge involved in it is, so I need to deposit an SMA spring on such kind of structures, or I can fabricate it and I can fit it based on the requirement. And second most important aspect of this is it should have a capability to arrest the vibration, and in the meantime, since it's a metallic layer, it should also have a capability to get actuate and it because of the heat. Okay, so these are some of the major concerns which we had in mind. So I should thank Dr. C.P. Paul. So he was generous enough. So when he heard this motivation, so he opened his facility for us. So one of our research scholar was involved in developing this work. So in this work, so basically we went for a laser additive manufacturing. Since we have a nickel and a titanium in our hand, and we thought that we will use these powders. So we fuse these powders in this laser region, and then we try to manipulate the laser. And when we try to manipulate the laser, we can get the structure whatever is required. So in order to so basically in this case is concerned, so we took a 2 kilowatt fiber laser. So fiber laser based additive manufacturing system which was deployed for a laser rapid manufacturing of various deposits, including nickel and titanium. So it consists of a 2 kilowatt fiber laser with a 5-axis workstation in a glove box and a computerized numerical controller, a coaxial nozzle, and a twin powder feeder. So the laser beam was transferred to the 5-axis CNC laser workstation through an optical fiber and a quartz lens to focus the beam at the laser workstation. A defocused beam of diameter 2 mm was delivered at the substrate surface, and a pure titanium plate of size 100 mm by 100 mm by 10 mm thick was used as a substrate. So the titanium substrate is chosen for our experiment is expected to for an easy debonding, as well as it can take care of the thermal expansion because of the difference in Ni and Ta. So prior to the experiment, so we just cleaned the sandblasted our system to roughen the machine surface so as to increase the laser absorption. So an argon gas was used as a shielding and a carrier gas, and it prevented the oxidation. So basically we took an 1:1 ratio of nickel titanium. So there are 3 different combinations with 3 different powders we do. So basically one combination is something like our main prime focus is to check its composition capability. So with respect to variation in composition, how does it behave? So there are 3 different NITA compositions with powders and 3 different weight percentage. So one is with NITA 45-55, another one is NITA 50-50, and another one is NITA 55-45. In addition to this, in order to, since our main motto is to have an actuation, so we should have some kind of ductility. So we went for a kind of a ternary composition. So in this ternary composition, we mixed with NITA, CU, etc. Okay. So in order to optimize the process, the number of tracks were deposited at different process parameters. So after deposition, the process tracks were examined and the uniform track which was analyzed. Okay, so basically as a first stage, so these are some kind of structures which we could fabricate it. So we attempted to fabricate some kind of brick kind of structures, and we also attempted to fabricate some kind of ring kind of structures which is of our own interest. Okay, so now since we are using a powder, our main motto would be to investigate the influence of process parameter. So one of the key parameter is the particle which is chosen. So the powder particle, almost like Ni and Cu powders had a powder particle within the range of 45 to 106 micrometer, whereas it also has a range of 75 to 150 micrometer for titanium. So these range of powder particles were selected for the experiments, and the powder particle have a bigger size and have a range, results in a semi-fused particle due to a smaller absorbed laser energy per unit one. So the powder particle which were chosen were spherical in shape, which is pretty evident from the same micrograph, as the spherical powder particles yields good density with no porosity in comparison to the regular and the flake shaped particle. Now, when we talk about this effect of these process parameter, as far as the laser additive manufacturing process is concerned, this process is basically governed by the laser power, then the beam diameter, then the material feed flow rate. Then we can also talk about the scan speed. Okay, so the shape and deposition of the tracks are governed by two combined parameters, like laser energy per unit area and the powder feed per unit area. So if I try to talk about the laser energy per unit area, it is basically defined as, like, if I try to correlate, so it is something like it depends upon the beam diameter of the surface substrate as well as the scan speed. So the shape of the track geometry were investigated in terms of the aspect ratio as a function of the deposition per unit area. So the experimental observation confirmed the formation of non-uniform discontinuous track under certain onset values of powder feed per unit area. It is just because of some minimum amount of laser energy is needed to assess two physical processes using the laser material interaction. So these processes are melting of feed powder and wetting of the thin layer of the substrate previously deposited material. So in the case of lamp of brick shaped structure, so only process parameter yielding to uniform and regular shape were screened in, and as the powder feed increased, so the laser energy per unit area was considered to be around 0.1 kilojoule per mm square. So for all as the powder feed increased, the laser energy also need to be increased as more the laser energy required to melt the powder fed at a high quality feed per unit area. So it was also observed that the various output across it was also observed that the various output in cross section of the track geometry were obtained with different combinations of laser energy and the powder fed per unit area. So basically this shows the track geometry in the prescribed form of the aspect ratio with respect to the ratio of the width and the height of the track. So it was also observed from this graph that the aspect ratio of above 5 were capable of depositing a defect-free track, as it was avoiding the inter-run porosities generated on the base of the two track due to the lack of fusion zone, and hence the process parameter yielding to the aspect ratio more than 5 were chosen for the experiments. Okay, now these are some of the kind of surface morphological analysis which we have performed with respect to these kind of structures. So as far as in this structures is concerned, so we took a microstructure analysis as well as an SEM analysis. So in this, like, we had the microstructure of TINACU samples developed by LAM in different compositions, and basically it provides a cross section of that sample. So like it shows the microstructure which is greater, and the samples were cold mounted on a polished, shows a microstructure of TINACU, it is uniform, and a dendrite microstructure which is due to higher cooling rate. Whereas in this case, if we see, so this is a kind of, so basically this belongs to NITI 45, this belongs to NITI 50, this belongs to NITI 55, and these are the combinations with respect to TINI CU5, TINI CU10, TINI CU15, TINI CU20, TINI CU25, and TINI CU30. Okay, so if you see, so this will give us a clarity with respect to the uniform and as a dendrite microstructure, which is due to the higher cooling rate. And as and when we try to increase the TINICU10, which gradually gets bigger than the TINICU5, and the mild deposition of precipitates like structures are visible, which might be due to the improper powder melting. And as far as TINICU15 is concerned, has a very large while comparing to the other samples, and the presence of porous at isolated locations are observed. So this might be due to the improper melting of the powder particle due to the laser additive manufacturing based structures. So when we try to closely observe the AFM analysis, so where we could see, like we could map our grain size with respect to the surface roughness. So what we are trying to study. Okay, so because as far as in our case is concerned, so the surface roughness is of least botheration, so we don't need to worry about as far as the surface roughness is concerned. Okay, so as far as in this material characterization is concerned, so the samples of these of these laser additive manufactured structures were cut transverse to the direction of the laying and prepared using a standard metallographic technique, and a microhardness measurement was carried out at an incremental distance of 25 micrometer at a load of 500 gram. So as far as in this case, the average microhardness in the case of NITI structures is in the range of 380, 440, and 525 VHL. So the value of this microhardness is more for a titanium rich sample, and this might be due to the formation of hard face caused by the increase in the titanium content. Now, when we talk about the microhardness of the ternary alloy, the NITI samples fabricated by this technique showed a microhardness in the range of 237 to 297 VHL. Okay, so the microstructure hardness in these kind of sample increase with increase of copper concentration, and the higher concentration of copper causes the formation of precipitate like TINICU2 and NI2, which basically attributes to the incremental of microhardness due to the internal stress. But in the ternary alloy with the inclusion of copper, the problem could be overcome as a variation in hardness, and it is not uniform across the sample. So this is almost a clear indication that a good alloy formation has been formed with this. Now, in order to study the mechanical test, so we went for a compression test. So as far as in this for this compression test is concerned, so again we did the compression test for both NITI and NITSU based structures, where the mechanical properties of the sample as a compressed test was carried out, and the samples were as per the ASTM 9 with the dimension of 5 mm dia and 10 mm length. At least 3 samples were tested. Okay, like in the case of elasticity of the material, like if you see, like the elasticity of the material formed are low due to their brittle nature, and all 3 samples are comparatively uniform. So as the percentage of titanium increase in the alloy, the elasticity gradually decreases, and the amount of ultimate strength increases as the percentage of Ni increase in the alloy. Thus, it is clear that NITI 50 has a better elasticity among the 3 binary alloys, which is the calculate moduli is in the range of 20, 21, 21, etc. So in the case of a ternary alloy, it is clear that the elasticity of all the samples have reasonably improved comparing to the binary alloy developing there. So there is an uniform and smooth growth of the curve initially for all the samples, gradually for NITI CU5 and NITI CU10. Then after reaching the yield strength level, the formation of the plateau is seen, which is quite similar. So this presence of this martensite orientation drives the transition curve to a plateau formation in the sample. Impact of the residual stress generated by the slip prevents the stress strain curve from attaining the maximum ultimate strength limit to be attained, and the remaining samples had a very low ultimate strength due to the defect of the precipitate form. So like as a result, the impact dislocation due to the compression stress test is also expected to be high for such kind of systems. Okay, now when we try to talk about the structural analysis, one of the key parameter with respect to shape memory alloy is the formation of this beta phase. So as far as this formation of this beta phase is concerned, so these beta phase is going to play a major role, which basically confirms that there is a kind of shape memory effect which exhibits on this surface. Okay, so which was evident with respect to NITI structures as well as with respect to NITI studio structures. So basically this confirms that so we have a kind of shape memory alloy effect which is being formed into it. But when we try to fabricate the structures as such, and when we try to put it in the field, so within no time there was a breakage was observed, because the results says that there is quite a good amount of brittleness is there. So in order to avoid that, when we try to investigate into it, we could understand that there were some kind of non-uniformity in the structure. Okay, so this non-uniformity is happening because of the exothermic reaction which is being generated between the NITI and CU structures. So because of this, there was some kind of amorphizations here and there. In addition to that, there were some kind of residual stress which was being generated in that region. Okay, so what we thought is, so we will go for some kind of post-processing. So since we have a laser in our mind, so we thought we will go for a laser-based post-processing. So one technique what we employed is a kind of a laser-based peening, and the other technique what we employed is a kind of a laser-based annealing. So with respect to laser-based annealing, we thought we can somehow eradicate the amorphization, and we can also relieve the stresses. And in the case of laser peening, so we try to induce a uniform stresses along the surface to get a proper structure. So this is a comparison which basically gives us a clarity. So as far as functional characteristics is concerned, so as far as shape memory alloy is concerned, so the major functional characteristics, one we call it as DEC, which is a differential scanning calorimetric analysis. So this scanning calorimetry analysis basically gives us the exact austenite start, austenite finish, and the martensite start, martensite finish. So with respect to application perspective point of view, so this will give me a window when my sample will get actuated. So with this, what is the temperature range in which exactly my sample gets actuated? Okay, so this is with these are some of the observations with respect to NITI 50-50 combinations, basically with respect to binary alloy, and these are the observations with respect to ternary alloy. So in all these cases, so we have optimized the parameter for laser peening and as well as laser annealing. After that, we got these results, where after laser peening and laser annealing, the NITI structures, the binary structures didn't give a proper fruitful result. In fact, this phase transformation property is indicates the formation of the improper structure. So this is visualized in the DSE, and there is no phase transformation curves which is seen. So as far as this austenite start temperature is concerned, it is at 2 degrees Celsius, and the austenite finish is around 21 degrees Celsius. Likewise, martensite start, if we look into it, it was something around 5 degrees Celsius, and the martensite finish was getting something around minus 15 degrees Celsius, which was not quite evident from these graphs. So whereas when we try to go for an improvement in the structure, so like we took the curve on both heating and cooling, where there was a kind of improvement was revealed with respect to NITI CU structures. Like in the case of NITI CU, the austenite structure was in the range of 23 to 28 point, austenite start was in the range of 23.81. and austenite finish was in the range of 24.55. Similarly, in the case of martensite phase, it was in the range of 23.07, and it ends at 22.07. So with respect to variation in composition, so we could understand the phase transformation. So this is the phase transformation, what we observe with the conventionally available sample, which confirms the formation of a proper beta phase P, and this also confirms the formation of the austenite to martensite. So similar observations were observed with respect to the additive manufactured sample. Okay, so one of the key application now, when we come back to our motivation, so one of the key application which we need to look into it is like our shape memory effect is confirmed, whereas we need to study how the storage modulus plays a major role. So for that, we did an analysis called as dynamic mechanical analysis. So this dynamic mechanical analysis will gives us a clarity about the storage modulus. So like this, considering the elastic energy, the storing properties of the material, the properties we are analyzed on cooling and heating measurement by using several frequencies of applied dynamic force. So basically the structure will look something like this. If this is our sample, we try to mount it and we try to apply a dynamic loading in this structure, and we also study the austenite. So from this we can estimate what is the austenite phase and the austenite start and the austenite finish, as well as the martensite start and the martensite finish of the structure. So this is not similar to what we called as Young's modulus. This is almost away from the DSC. So among the formed sample from the phase transformation property analysis, so DSC clearly gives a clear indication that on the only one of the binary alloy, 2 ternary alloys, the 3 samples were characterized with DMA, and DMA results of these samples showed that the storage modulus was measured in the range of -30 to +30 for all the samples, and the measurements were performed with single heating and cooling cycles, where we could estimate where the storage modulus was getting activated in the range of 75 degrees Celsius. Okay, and this was one of the key parameters which helped us to fit our system into the quill, and we could study the structural as well as actuation aspect of this with respect to industry 4.0 environment. Okay, so with this we are closing the first module. So any questions or any doubts in this?
The participants, please write your question on the chat box also, if you want. Or otherwise, unmute yourself and ask the question.
Okay.
Yeah, so, since there are no questions.
No questions.
Dr. Palani,
Okay,
please,
we will
continue. Yeah.
Okay. So we will go. Yes, please.
So what kind of application you are using the shape memory alloys?
For this kind of application, where we can arrest the vibration in a spindle and we can actuate the shape memory alloy to arrest the vibration.
Okay, sir.
I think you are not clear with the application. I think so. Like for example, you take a drilling machine. Okay, so in your drilling machine, if the tool is going to fail, 2 different effects will come. So one is with respect to heat, another one is with respect to vibration. Okay, so what we are trying to do is, so we have a tool holder. So over the tool holder, we are fabricating these shape memory alloy structures. So what happens is when the tool is when tool starts generating the heat, this structure will try to actuate and it will try to arrest the vibration. And in the meantime, so we have a kind of an infrared camera over here. Through the infrared camera, you can sense that the shape memory alloy is actuated. So I need to think of changing my production line. Is it clear? So this is one application which we are focusing. Okay, like similar to this, you can develop such kind of smart sensors wherever you have a heat as your input for sensing the failure or sensing the response. Like one example is most of you might have seen a 3D printer, right? So in a 3D printer, the major problem is blockage of nozzle. So how do you predict the blockage of nozzle? So one option would be when the particles start depositing it inside your nozzle, or when the particles start coagulating it inside your nozzle, the nozzle temperature will increase. Okay, so if we have a sensor over there, so that we can estimate how much is the temperature, and based on that you can predict it and you can take care of the failure.
Okay, sir.
Okay, so shall we go to the next case study? So the next case study is something related to a wire arc based additive manufacturing. So as far as in this wire arc based additive manufacturing is concerned, so again, we were more concerned about developing a device which is called as a small micro gripper. So as far as in this micro gripper is concerned, so let us consider I have a shape memory alloy which I have fabricated in the form of a circular ring. I'm just dicing it into two. So both these splines, I'm just putting it over here. And then there is a gripper which is available. So what I'm doing is I'm just actuating it. So when I try to actuate, it becomes straight and it will hold the object. So when it tries to hold the object, and when you try to cut off the heat, so it comes back to its state. So that is how we can initiate a two-way actuation in this. Now, the interesting part of this particular system is like, suppose I need to use it in some kind of reserved environment where I cannot use a power supply. There, I can use a hot water. I can just push an hot water inside for actuation. This is one aspect. Another aspect is I can use a laser so that at a distance environment, I can just actuate my system. Okay. Now, you might why we didn't use the earlier system. What we could observe is in the earlier system, in fact, we could get the property, but when we try to look into the reliability and life cycle of the shape memory alloy, what we have fabricated, it was very difficult for us to use it for a longer life. That is because like we are having two powders. We are trying to fuse these powders to make it in the form of a shape memory alloy. So internally there are some kind of exothermic reactions which was coming up when during the heating cycle also we could observe that it was initiating some kind of failure on the surface. So in order to avoid that, so we thought of developing our own additive manufacturing system. So this is a simple MIG based additive manufacturing. We call it as wire arc based additive because we use an NITI wire which is commercially available, and we feed the wire through a MIG gun. We manipulated the structure. So we developed our own XYZ stage, and this XYZ stage is fed to a controller where using a CAD model, we can convert into a CNC code, and that CNC code is fed into the XYZ stage to create the structure. So the flexibility of this system is we don't need to worry about maintaining the powder composition, etc. All those stuff. We get the wire. So this machine has a capability to use a wire in the range of 0.8 to 1.2 mm. So we can just select in that wire dia, we can feed it and we can fabricate the structure. Okay, so in fact, this is a small video which shows how it tries to build the structure. Okay, so we dedicated this machine basically for shape memory alloy so that we can build customized shape memory alloy structures. So that with that as an idea in mind, we developed it. Okay, and interesting part in this is, like we all know, the crystallization or the structural aspect of it basically depends upon the substrate heating. So we employ two different substrate heating. So one is something like it has a capability, the substrate heating has a capability to heat from room temperature to 600 degrees Celsius, so that we can take care of the crystal structure which is being generated. Another one aspect is, since we had a cooling bed, so what we did is we pump this cooling bed has a capability to pump liquid nitrogen inside it. So when we try to pump a liquid nitrogen inside it, so that also will have its own effect in taking care of the crystallization. So it has a kind of a turret based rotary system. So in this turret based rotary system, so we have kept these two substrate heating systems so that we can
Hello.
So we just make it in the form of a thin
Dr.
section.
Palani, we lost you, so can you maybe explain from the last slide?
Acha, from this?
No, not like that, not like that. Can you go further? Friend, yeah, from here.
This one?
Yeah,
Okay. Is it okay now?
It is okay. The second time it is happening actually.
Acha.
It's okay, no problem. Please carry on, no problem. Please.
Okay, so as far as in this wire arc based system is concerned, so we could try to manipulate two different heating bed systems. So one heating bed system is something like it has a capability to vary the temperature from room temperature to 650 degrees Celsius, so that we can take care of the crystallization during the building of the structures. Another one is, so the bed had a cooling arrangement where we can just feel the liquid nitrogen inside it, or pump the liquid nitrogen inside it, so that we can take care of the crystallization behavior in that structure. So we had a kind of turret mechanism so that we can fix into these structures. Okay. Now, as far as the sample preparation is concerned, or the methodology what we followed is basically like we built an NITI structures. So using an wire EDM, we try to make a small pseudo-elastic NITI structures, and then we anneal it, and then so that we give to activate the SMA based behavior. So by applying a stress, we can have a D-twin martensite, and as well as we have a austenite phase. So with comparing these two, we can achieve an actuation. So that is what the idea we had in mind. In fact, it was a bit flexible for us, because whichever sample we could fabricate, we could evidently see the actuation coming out of it. Okay. So in fact, I'll be going in detail into the how we have we could predict our actuation and how we have analyzed our actuation. Okay. Now, before going into this, like as far as let us look into this additive manufacturing perspective point of view, this is kind of a crude method. Okay. See, in fact, from our group, it was the first of its kind from our group, which we have come up with this technology of fabricating NITI structures using wire arc. So, in order to get a metallurgical ground of it, so we had a collaboration with the Russian university, basically from St. Petersburg University. So they have been working on powder metallurgical based NITI structures. So they have a strong background towards metallurgical aspect of the shape memorial structure. So we collaborated with them to understand the mechanism, what is happening in it. So as a first level of understanding, so what we did is, so we made some structures. So these structures, something kind of, we made a 5-layer structures. In fact, this is a kind of a panoramic cross section of the 5-layered sample. So for convenience, the layers were numbered from the bottom to the top. So that is, the first layer was the layer deposited on the titanium substrate, and the 5th layer was the last layer deposited on the layer. So like we could easily fabricate the structures, and in fact, when we tried to analyze it, there were no cracks were observed in the structures, because in most of these cases, what we did is we used a substrate heating of something around 250 degrees Celsius in order to maintain the homogeneity. So in order to understand the behavior of it, the first layer was like we took the sample at different points. So one is like we took the sample at the left, we took the sample at the center, and then we took the sample at the right, and we try to analyze the microstructure behavior of it. So this is the closer view of the microstructure. So in fact, this is the closer view of the microstructure, what we could get from it. Like in the first layer, there was a mixture of 2 phase, basically a dendrite matrix and an interdendrite space, which was available. And along a long columnar grain with a length of few millimeters have been formed at the intermediate layer. So usually this intermediate layer, the intermediate area of the VAM contains the columnar grain that grow throughout the layer. At the same time, in the present sample, the columnar grain grew within one layer, and the precise interface between the layers were formed. So during the deposition of the consequent layer, some part of the previous layers was remelted and recrystallized together with a new layer, and this has led to a formation of a clearly visible remelted zone between the layers on top of the 5th layer, and the equiaxed zones were observed. So the same zones were found on top side of the 3rd and the 4th layer, and near the side of the surface, which are not subjected to the remelting during the deposition of the consequent layer. So from this, we can say that the structure of the NITA along the cross section is typical to the alloy produced by the VAM, and the mechanism of the grain formation are similar to the are almost uniform to all. Now, when we try to talk about the chemical phase composition of these NITA structures, so basically we took a SEM and a EDAX analysis, and then we also had some kind of mechanical analysis. So the microstructure and the chemical composition in the different layers of samples were studied with SEM, EDAX, and an XRD. Like the SEM image of the first layer structure, it has been seen that the 2 phases are observed. One is a light gray phase, which is marked as A. that looks like a dendrite matrix, and a dark gray phase which is marked as B, which looks like that occupies the interdendritic space. So the EDAC analysis also shows that the chemical composition of this light gray phase is almost 52% of titanium and 48% of nickel, which corresponds to the titanium rich Ni phase, because we have a titanium substrate. However, the dark gray phase consists of 67% at percentage titanium and 33% of nickel, which corresponds to the Ti2 Ni phase. So this is almost confirmed from the X-ray diffraction analysis, showing the reflex of the B19 phase which is available. So the quantitative analysis of the SEM image of the first layer performed by the system. So we could see the fraction of NITA phase which is available and was about 75 plus or minus on an average. A large amount of Ti2 Ni phase was observed, and the first layer and the precise interface was visible between the first and the second layer. So whereas when we try to closely observe the SEM images of the layer on the second, third, and fifth, it shows the presence of the columnar grains in the inner layer having an internal dendritic structure. So this is similar to the first layer, but with similar size of dendrites and the interdendrite space. So this also shows a kind of a secondary layer with large volume of gray space, where a small dark gray dots are distributed through the whole volume. So the EDAX data shows the chemical composition of the phase marked and at 51% of titanium and 49% of the nickel. On the other hand, the dendrite space marked D basically confirms that there is a kind of 49% titanium and 50.3% nickel. Okay, so the interesting part in this is, so this is with respect to the second layer. Now, when we talk about the third layer, so this is our third layer. The interdendrite space includes two phases, white area marked as F and dark area marked by G. So the EDX result shows that the volume have different composition, and the phase marked by F is a titanium rich NITA phase with Ta concentration of 52.3%, whereas the area marked by G are Ni rich NITA phase containing of 51.3% nickel. So the main volume of the third layer was occupied by the dendrite matrix, which is an Ni rich NITA phase having 49.5% of titanium and 50.5% of nickel. So the fourth layer composes of the structural and the similar to the third layer. However, the dendrite matrix has a chemical composition of titanium with 50.9% of Ni, and the volume fraction of Ni rich NITA phase in the interdendrite space could be achieved. So now, if I talk about the fifth layer, so this is my fifth layer. So in this fifth layer, the composition is something like that the interdendrite space does not contain any the Ni rich and the NITA layer, and in this layer, the dendritic matrix is Ni rich NITA phase, which Ni concentration of 15.9% marked as K. Okay, and the white volumes are marked as L, which are the equiatomic NITA structures. So therefore, it is in a nutshell, if I would like to say, like even though I have built the structures, so I could ensure there is a proper uniformity in these structures, even though there are some kind of minor inclusions which are there, but still it is considerable enough for me to take care of my system. Okay. Now, the one of the major key aspect with respect to the DSC analysis point of view. So in the case of DSC analysis, we could get a clear a martensitic transformation in these NITA samples which is produced. In fact, we could get a better clarity. In fact, we could easily map with our beta phase and with respect to the austenite phase and the martensite phase with respect to the cooling characteristics. So this confirms us that there was a proper NITA phase which was getting generated along the structures. So in fact, this NITA structures were checked, the martensite and the austenite transformation which was happening on the structures, which was checked at each and every layers to see how does it behaves. So basically, when we try to observe like the martensite and the transformation region, the L1 layer had a better impact, whereas at the L5 layer, almost there was a reduction in the martensite phase which was observed, and a further increase in the structure resulted in some kind of variations along the layer. Okay, so with this as an idea, so we were trying to predict, in fact, we did some kind of stress strain analysis. So in the case of a stress strain analysis, we could observe that that NI distribution were along the layers, and it does not depend upon the location, and cut along the samples to estimate the NI concentration across the layer. So we used the martensite temperature which is present as compared to the martensite transformation which is available. So as far as in this NITA layers, so we could observe that the first layer, so this was the mechanism which we could initially observe, that when there is a titanium layer which is available, so when we try to go for a deposit, there was a formation of nickel and a titanium plus titanium layer which was coming out from the substrate, so which was large enough to rapidly absorb the heat on the first layer. So in this regard, the first layer experience a high cooling rate that prevent in the growth of the columnar grains during the crystallization of the second and further layer. The epitaxial growth grain occurs and eventually lead to the formation of the larger columnar grains. So on the top area of the second and the next layer, the equiax grain size were formed. And however, these zones are completely or partially remelt during the deposition of the consequent layer. And these remelt zones solidified together with the consequent layer, leading to the formation of columnar grains. And the top region of the fifth layer has retained an equiaxed grain, as this region was not remelted unlike the other layers. So if I try to, in a similar fashion, we could see the structure of the fourth and the fifth layer were so close to each other. Consequently, these layer underwent this B2 to B19 martensitic transformation, the same temperature range. Moreover, the chemical composition of these dendrite matrix in these layers was close to the composition of the wire which is used in the deposition. So the interesting part in this is, like, where we could observe that at third and fourth, beyond second layer, you get a proper uniformity. Whereas in the first and the second layer, we have an influence of the titanium substrate, which was coming out of it, even though we have employed the a substrate heating in this region. Okay, so with this as an idea, in fact, we did a kind of a stress strain analysis to study the pseudoelastic behavior as well as to study the austenite state and the austenite finish of the surface, where we could observe that with respect to pseudoelasticity property, it was behaving in a very good way. Whereas with respect to shape memory alloy property is concerned, we could have a better actuation characteristics coming out of it. In fact, this is a video which we were involved in fabricating a kind of a spring kind of structure. So this is a kind of a wire arc based additive manufacturing head. So in this wire arc based additive, there is a kind of deposition which is happening, and this rod, currently it is not heated up. However, it has a capability to get heated up with respect to an electrical biasing, so that you can heat it and then you can go for a deposition. Okay, so one of the key aspect of this, so one of the key aspect of it which I would like to explain over here is, or I would say the outcome of this work is, basically we could understand, in fact, we currently more investigations are going on in this direction with respect to influence of temperature, influence of substrate temperature, influence of substrate, of different substrate. Like currently we are using a titanium plate, so we need to go for a Ni rich system. So we are also looking for a Ni based plate and to see how the Ni rich system works, because for most of the biomedical application, Ni plays a major role. And we are also looking into some kind of stresses which are being involved in it. So currently we are focusing on this type. But as far as actuation perspective point of view, like if I need to come back to my earlier motivation, where in this case, I require a thin sections. So in most of these cases, so my minimum feature size, what I could get is something around near to around 1 centimeter or close to around 1 centimeter. And I need to go for an EDM cut to make the structures, and then I need to actuate it. So in order to avoid this, we thought of using a technique called as a laser assisted hybrid wire arc based additive manufacturing system. So as far as in this laser assisted system is concerned, like as far as in our MIG based welding system, like if this is my sample, so there is an arc which jumps and it tries to deposit. Now, when an arc jumps on the surface, so the surface also plays a major role in manipulating my arc. So what I can do is, if I have a sample, if I try to make a small laser marking on this region, then I can somehow concentrate my arc in this region so that I can make thin sections. So with this as an idea, we thought of developing this system. So in this system, we had a small 50-watt fiber laser. So using a 50-watt fiber laser, basically it's a kind of a marking laser which we used. And this 50-watt fiber laser was used for depositing. So like what we did is like we used a different parameters, and these parameters were used for creating such kind of lines. So the laser what we used had a galvano scanner in this. So using a galvano scanner, we can manipulate our system so that we can take care of the track. And with respect to the track, we can so the major key parameters involved in this is like the track width, then the number of passes, and basically the trench. So these are going to play a major role with respect to focusing my arc in this particular domain. And when I try to focus my arc, so I can fabricate thin sections out of it. So with this as an idea, so we started our work by changing the different process parameters. So these are the different process parameters which we have employed for creating a marking on the titanium plate. So one is with respect to number of passes, with respect to laser power. We studied the depth, we studied the roughness, and using a contact angle measurement, we were trying to investigate the average contact angle. Basically, this the idea behind this is like not only we are trying to concentrate the arc, we are also trying to focus on the droppability of the particle which is available. So basically the wettability of the particle which falls on the surface, and with respect to that we were trying to study the overall behavior of the system, and we were trying to take care of the track width coming out of it. So in this case, like the roughness of the substrate basically plays a major role. So the in most of our lasers, so we will be using a TM01 mode beam, which is a shallow groove at the center of bottom with a more in depth at the sides. This TM01 mode allows a concentration of the lower energy at the center of the beam and more energy at the edge. So the roughness profile reduced with an increase in the number of laser passes due to the consistent impact of the laser beam, irradiation, and the rapid vaporization of the material. So the roughness. Yes, sir.
Sir, kindly repeat the last slide, sir.
Acha, in this?
Yes,
this
sir.
One?
Yes, I didn't understood what you're trying to say.
Okay.
Okay, sir.
So let us talk about this. So in this case, I have a sample. Okay. So what I'm doing is using a laser marking, I am creating a mark on the surface. So when we are trying to create a mark on the surface, so this will be the focal point where we can just attract the arc towards the center. Okay. So when we try to attract the arc towards the center, we can manipulate the arc and we can get a thin sections out of it. Okay. So to give you a better clarity, so this is the arc without marking. This is the structure which we have fabricated with wire arc without laser marking. And this is the structure which we have fabricated with laser marking. So without laser marking, your width is something around 3.5 mm, whereas with marking at the same parameter, your width is something around 1.8 mm. So this is because you are trying to manipulate the arc with respect to your surface roughness, which you are trying to induce on the surface. Okay. So for inducing the surface roughness, so what we are trying to do is we are using a laser as a key player for creating the mark. So for that, so we have a 50-watt laser. So in this 50-watt laser, this 50-watt laser is fitted with a galvano scanner, and basically it has a TEM mode of beam, which creates a shallower groove at the center. So TEM mode would be something like this. Okay, so if this is my surface, So I get a Gaussian beam profile in the form of a shallow groove at the center of the bottom with more in depth at the side. And these stem modes allow the concentration of the lower energy at the center of the beam and more energy at the edges. So the roughness profile reduced with increase in the number of the laser pass due to the consistent impact of the laser beam irradiation and the rapid vaporization of the material. In fact, the roughness of the substrate strongly modifies the wettability of the surface, and the wettability of the surface is analyzed in terms of the surface free energy, which we called as SFE. Okay, so like basically it is taken care by the contact angle with respect to the interfacial tension and the solid vapor phase. Okay, so with respect to this, so we are trying to initiate an interfacial tension along the surface. And when we try to initiate an interfacial tension, so we can focus our arc in that particular region to create the structure out of it. Okay, so our first study was to do, so we did a set of experiments. So basically we did a marking with respect to number of passes, and then we were trying to study the contact angle behavior of the system. So this is the closer view of the contact angle measurement, where we could see like how the contact angle behaves and how the wettability of the structure is being taken care, as well as the interfacial tension is also taken care. Now let us discuss about the microstructure characteristics of these systems. So what we did is, so we went for laser marking and we studied the microstructure behavior. So this microstructure, the marking was done on a titanium plate, and the microstructure after the laser treatment had a kind of an alpha TI and the presence of beta TI lamellae in the intergranular region before marking. So the as received microstructure suggested that it undergoes a cold roll process on the titanium plate, because these plates which we have procured from outside had some kind of cold roll behavior, which resulted in some kind of change in microstructure. And the average grain size was varied between 350 micrometer to 250 micrometer and 50 micrometer to 100 micrometer. Before the marking led to a signal which is also causes a circular alpha martensite formation. So like if I closely observe the XRD graph of the titanium substrate before laser treatment and after laser treatment. So before laser treatment, the mixture of alpha titanium and beta titanium belonging to the hexagonal lattice structure is present. However, after the laser treatment, the titanium oxide and the nitride are found belonging to the tetragonal and the monoclinic structure respectively. So this, when we try to observe this formation of these titanium oxide, the nitride is the reason where we could observe such kind of color change on the region. So if the surface temperature is held below the boiling point of titanium, so during the laser irradiation, the titanium surface product and the titanium nitride is expected to form a liquid titanium ambient gas reaction. Okay, so this laser marking was done in an open atmosphere. So an atmospheric nitrogen will react to the titanium substrate and form nitride with increasing the laser passes. And the temperature in the irradiated region of the sample arises, which enhances the diffusion of the nitrogen into the surface and decreases in the beta titanium content due to the laser surface melting, which is attributed to the stabilization of the martensite phase. Okay, so after a laser treatment, that is the reason we have some kind of structures which is coming out of it. Now let us discuss about how this effect of laser marking has an impact on the layers with respect to building up of the layers. So for that, we need to investigate the track geometry. So the first layer was the layer deposited on the titanium substrate after the laser marking and without laser marking. The roughness and the surface energy will change after the marking along with the depth of around 1.5 mm deep track will provide a path for an unstable melt pool. So the Ni concentration in the NITI wire used for VAM sample with a protection of 15.9. Therefore, the composition after second layer was close to the composition of the initial wire with or without the laser marking. On the other hand, Ni concentration in the first layer was lesser than the wire without the laser marked samples. So if we try to observe this, like initially Now, this is the layer which we are trying to get. So we try to build the layers. This will give you a closer view how the structures are being fabricated along the layers. Okay, so in fact, this is a kind of a closer view which depicts the BAM sample built with and without the laser marking. So the columnar grains were formed on the samples, built with and without laser marking. However, the sample without laser marking reveals a relatively coarser grain structure. So the grain size is found to be ranging in the range of 60 to 120 micrometer for without laser mark, and the 20 micrometer through 35 micrometer for marked samples. Whereas in the case of B and D, if we try to show the some elemental mapping result in a VAM deposited track without and with mark, and the different region rich in titanium and nickel are located at different layers. So in samples without laser marking, oxide layers are formed due to a low cooling rate as compared to the mark sample, and wide surface area in the laser mark samples lead to high heat flow to the substrate, and the previously layer leading to higher cooling rate. So at high temperatures, the titanium will react to the atmospheric oxygen, and the melt pool of wall built without marking will lead to more contact between the atmosphere and the melt pool, leading to oxide formation. So even with inclusion of such unexpected oxides, the VAM structure still has a structural and an elemental discontinuity. And when faced with a huge oxide island, a well pool bypasses island and changes the wetting boundary by an irregular curve until the well pool passes it continuously. So if I try to observe the average hardness out of it, so the average micro hardness of the single track of the VAM deposited NITI varies in the range of 200 HP to 350 HP, and it can be seen that the hardness of the bottom section is higher than the middle section and the top section. So the laser marking provides a larger cooling rate due to its large surface area and a high heat flow to the surface, and the middle section and the top section has revealed low cooling rate because of the low temperature gradient in the melt pool. So this laser treatment is done after each layer deposition for reducing the porosity and increasing the grain refinement due to its hardness is higher than that without the mark sample. So in order to evaluate the bulk mechanical properties of the sample, a compression test was carried out. So in fact, this is the characteristics of a compression test. It can be seen that the laser mark samples have a higher strength due to the grain refinement, lower porosity, and Ni-rich phase for the formation. So the results from the compression test are in line with the results obtained from the metallurgical characterization. And in order to study the electrical actuation, so what we did is we had a small system which we have developed in-house. So the main idea of this system is to study the electrical characteristics behavior. So we have just incorporated the structure in it, and then we keep the we keep some kind of load to it, and then we were trying to study the actuation characteristics of the as well as the life cycle behavior. Okay, in fact, I have a video which shows how does this actuation happens, and this is the overall life cycle behavior which we could achieve. So with respect to marked and without marked samples, so we could observe that the marked sample showed a better displacement as compared to the samples without marking. And in fact, the interesting part in this is, so you don't need to go for a post processing. Like in the earlier case, when we went for a direct wire arc based additive, so we went for some kind of post processing. So we may need to dice the sample and we may need to do the actuation. Okay, whereas in this case, as such, after the laser marking, we could take the sample and we can do the actuation. Let me just show you a small video which shows that how the actuation was performed. So this is an actuation where we could see like there is a plate. Over the plate, we have kept the thin section of NITI structure, and we are trying to actuate it. So this is a thin sheet which we have fabricated. So when we come back to our earlier motivation, one important aspect which we need to look into it is like how it is getting actuated at with a laser. Hope you could able to see the video. So here, this is the as manufactured sample. So what we have done is we have done the actuation using a laser, so that for our gripper application, so we can go for a non-contact based actuation. So there is a laser displacement sensor which is incorporated in it. So this laser displacement sensor will study the displacement variation, so that we can see how does the life cycle behaves. So any questions or any doubt in this? Sorry. So in a nutshell, we were just going through the different wire arc based additive manufacturing system. So in wire arc based additive manufacturing system, so we have investigated the overall this metallographical behavior in detail. So since it's an in-house developed system, so it's a promising system for developing an customized 3D printed structures, the laser-based 3D printed structures. And then we have integrated a laser to make thin sections out of it for different applications. Okay. Now let us go to, is there any questions in the chat box?
No, Dr. Palani.
No.
Okay. Let us go to the last case.
There is one question,
Please. Yes.
How does the final wire thickness affect the behavior of nickel titanium alloy?
Wire thickness means the wire diameter which we are feeding, right?
Yes.
Okay. Actually, see the machine.
No, final wire
Sir,
thickness.
Hello.
Yes, sir. Yes, please.
Sir, what I meant was like when you vibrate that final thin wall, sir.
Fabricate the thin wall.
Yes, sir.
Yeah.
So how does that final wall thickness affect the behavior of this?
Okay. See, like as far as this wall thickness is concerned, till now we could go up to 0.25 mm wall thickness. Okay. So this with the 0.25 mm wall thickness, the reliability of the of our actuator was getting deteriorated, because like if you closely observe this mechanism of this shape memory alloy getting actuated, see you are doing it in an open environment. So there is a switching between the austenite and the martensite, which is nothing but heating. So when there is a heating is there, it tries to attract oxide. So more amount of oxide will start getting infused into the structure, and at one particular point it will lose its shape memory alloy property. Okay, like for example, like if I need to explain, I will just explain with this cycle. On the initial cycle, there will be some kind of oxide which will fall on the surface, and then slowly it will deteriorate. Slowly we are cooling it so that it comes back to its surface. Then again I am heating it. So whatever oxide which was available in the earlier, even though because of the displacement it breaks, but still it will be a point to attract more amount of oxide. So less will be the feature size. Then you are prone to have a reduction in the life cycle behavior. Okay. Whereas in fact we have made a comparative study. So we could go from 0.5 mm to 3 mm thickness. So with 3 mm thickness, we could get a better life cycle behavior, and in fact it had a capability to lift more amount of load, whereas the response time was getting down with 3 mm, and with 0.25 mm your response time was quite good. So basically that is how you may need to narrow down with your application.
Sir, my reason for asking was this, sir. When we are trying to make this these thin walls, sir, we can form it like with just a single laser scan, or we can use multiple scan tracks.
And
So
actually, like it also like in this case, I am talking about the width of the wall. If I
Yes,
need to talk about the height of the wall, okay, so then I may need to go for a more amount of passes in my marking. Okay, so more passes in marking will result in a higher wall thickness.
Yeah, no, sir. Even if you're like, as my wall thickness increases, sir, even in a single layer, I have to scan multiple times, right, sir? No.
Actually, your substrate is sufficient enough. Okay. See, like when you try to mark it in your substrate, it takes care of your wall thickness towards the entire region. Okay, I will just show you this one. Okay, this is one observation where you could see, like this is with track width and track height, with marking and without marking. So this is with the marking where you could see your track height is increasing and your track width is well within the limit. Okay. Okay. So you don't need to do each and every time. Once you are done, it is sufficient enough. You can build your track structure.
Okay. Thank you, sir.
Dr. Palani, there is another question.
Yes.
What is the effect of heating multiple times on the life of SMA throughout the application.
Acha, like this heating means what I understand is there are two types of heating is there during the fabrication or during the actuation.
Here,
During
there
the
is
activation, sir.
During the actuation. See, like I would like to explain this question with respect to this particular video. Okay. So one video I have shown you where we have used a laser. So in this case, I have applied a load to it. Okay. So with respect to lifting your load, so you are trying to supply a heat to your surface. Okay. Now, suppose based on my application, if there is going to be a minimal load, then appropriately the amount of heat which I am going to supply will be less. Okay. So the amount of heat which I am supplying basically depends upon the thickness of the material, the displacement and the response time. Okay. So more we go amount of heat, then obviously in due course of time, we will lose our recovery ratio. Okay. So with respect to this, here the heating is completely on a different plane. Here it is something like huge, high amount of energy is bombarded on the surface. Okay, because we are using a laser. So even with a laser, when we try to go for a continuous actuation up to 2 lakh cycles, we didn't had any kind of issue with respect to recovery behavior. Okay, so that is an interesting aspect with respect to shape memory relay. So in a nutshell, I would say that your shape memory relay is quite reliable with respect to the heating characteristics.
Okay, thank you, sir.
Sir, I have a question.
Yes.
So this blocks that you've deposited and those for sectioning, you would have gone for bi-radium, right, sir?
Yes, sir. Sir, I couldn't get your hello. Your voice is breaking. Hello.
Hello, is it clear now, sir?
Hello.
Hello, is it better now, sir?
Hello. No. Hello.
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 hello. Is this Shanmugha Priya?
Yes, sir. Hello.
Yes, Shanmugha Priya, please.
Is the voice clear now, sir?
Now it is clear. You please.
Okay. So the tracks after deposition, while taking it for different tests, you would have sectioned it using bi-radium, right, no, sir?
Yeah, I have sectioned it using wire radium.
So will that not affect the hardness in the specimen plate or those sections? These are very thin sections.
And actually, as far as in this case is concerned, like one option, what we went is like whichever we have gone for 0.25 mm, we are going for a chemical etching, and then we are trying to do the analysis. Wherever we are going beyond 1 mm, okay, so for that we are going for a wire radium, and we didn't face any issue with respect to the stresses which are being generated using wire radium, because 1 mm is okay.
Okay, sir.
Dr. Palani, there is another question.
Yes, sir.
Could you mention some sources of SMA in India?
Currently, on a government perspective point of view, there have been talks where IITI is trying to develop a mass production based shape memory alloy. Okay, but somehow they have not marketed it. Soon, I think in this year it might be on. So there is a supplier from Gujarat who provides us shape memory alloys. Apart from that, there is a trader called Veera's Traders from Hyderabad. So normally we try to get it from him. So he is a local supplier who try to get shape memory alloy from India. Okay, but apart from this, in case if you are looking for some kind of thin film, or in case if you are looking, there is a concept called bimorph. So if you are looking for bimorph, we can supply it to you. So we have a production capability in our lab to fabricate up to 1 meter by 1 meter area. Okay, so which has this shape memory alloys has a potential application towards high frequency. Okay, so this is an indigenously developed system, so which we can supply it to you. Normally for college teachers, we give it at free of cost so that they can use it for their experiments and as well as for demonstration.
Okay, so you make alloy and you sell
Yeah,
as
we
a solid
fabric
component. Yes.
in the form of a bimorph thin film.
Okay.
Bimorph based actuator, we sell it. We said no. I think I should not say we are selling it. We are giving it.
Okay. Yeah. Let's say, so whatever you mentioned, where on Mithani, they are selling both wire form and powder forms, right?
Yeah, but not on a small scale. So
okay.
it because they request us to send in something near to around 15 kgs. So if we need to buy, we need to buy it in a 15 kg wire. Okay, whereas the Veras traders, who is in connection with some of the local suppliers, so he sell it at a lower volume. He's from Hyderabad, so he sells.
Okay. Thank you.
So shall we continue with the?
Yeah, please. Yes.
Okay. So now the next level one. So till now we were more looking into this what do you call on a macro level. Okay. Now we will slightly move to the micro level, where this is a completely a peculiar technology which I would like to discuss in this forum. So this technology is used for printing. So like normally in your printers, like some kind of inkjet printing are there. So these inkjet printings are capable enough in printing some kind of circuits, etc. So similar to this, we are using a laser. So we are manipulating these laser systems. In fact, we have developed our own unit to print microstructures. Okay. So the mechanism behind these structures or this system is called as laser-induced forward transfer. So as far as this laser-induced forward transfer technique is concerned, so we all know a light which is falling on the surface. When a light falls on the surface, it has three different phenomena. One is an absorption, another one is transmission, and the third one is reflection. So these characteristics are well taken care by the material. So any material, if you take, so it will have an absorption coefficient. So, it has an based on the absorption coefficient, you can estimate the transmission and the reflection. So some material will be absorbing the light in the infrared region. Some material will be absorbing the light in the ultraviolet region. So such kind of wide spectrums are there. Okay. So with this fundamental, if we closely observe, let us consider I have a glass through which the light is passing through it. So I'm just keeping an absorbing layer over here. So the main function of this absorbing layer, it will absorb the light and it gets heated up, and there will be a kind of an expulsion, or there will be a kind of a removal of the material, which will result in expulsion of the surface, which it will push the material, which is coated on it in a forward direction. Okay, so when we try to nomenclate, this is the absorbing layer, which we call it as sacrificial layer. We have a donor film, and then we have an acceptor film. So this is what is the mechanism of laser-induced forward transfer. That is, we are transferring the donor film to the acceptor film. Now, I am just correlating this with respect to 3D printing. So where I have an acceptor film, which is nothing but a stage, which can be manipulated at XYZ direction. Similarly, a donor film is there, which can be manipulated at XY direction. So that when we try to manipulate it, and when we just have an interfacing to our laser system, we can precisely control the spot. And when we try to precisely control the spot, we can transfer the particle and we can collect the particle. Okay, so we can print the particle using this inkjet printing concept. Okay, so just to give you a clarity, in fact, we were more looking into the particle dynamics, how the particle dynamics flows from one region to another region. So this is one particle dynamic experiment which we did in our laboratory in collaboration with one of our Japanese counterpart to study how does the particle flow from the donor to the acceptor. Okay, so this is a kind of a shadowgraphic concept. So in this shadowgraphic concept, we see, so this is our donor region and this is our acceptor region. And from the donor region, the laser is interacting. From the particle is moving in this direction and it is getting collected in the acceptor region. Okay, so the major parameter involved in this is our laser fluence as well as our spot overlap. Okay, so this will take care of the transfer of the particle from the donor region to the acceptor region. So in fact, here in this case, the laser fluence is quite heavy, which is around 550 millijoule per centimeter square, which is resulting in a high amount of velocity coming out of it. So because of this, what is happening is when the velocity moves at a very high speed, it will damage the acceptor and the donor. Okay, so we have reduced our laser fluence to 250, where there is a transfer of particle from the donor region to the acceptor region, where we could see there is a kind of laser interacting on the surface which needs to be transferred, and there is a kind of melting which happens. And the third, this is an efficient one, which will give us a clarity. So where we are making a thin nanostructures and using a laser, we are just irradiating it. The sacrificial goes off. Here we are using a sacrificial layer as ITO, and the transfer of the particle will happen. So this transfer can be on a large area or it can be on a small area. Okay, based on the size of the laser, what we are using it, and we could estimate the velocity was something around 200 meter per second velocity, which we could estimate. Okay, and then we slowly reduced our laser fluence to see how does the particle moves. In fact, at 50 millijoule per centimeter square, where the laser fluence is less, we could see the particle which was just falling on the surface without any impact of the laser on the material. Okay, so from this study, we could get an understanding that this system is a very good system where we can transfer any kind of structure from one region to the another region. For example, I have, you might have, nowadays people are working on this flexible electronics, wearable electronics, etc. In all these places, you are using a textile, you are using a textile material, you are using a flexible PET materials, etc. It is very difficult to build a structure, a high melting material on it. Whereas we can develop a high melting material in some other region, and then you can transfer this high melting material on these wearables or flexible structures. So this is one of the promising technique what we thought of. Now you might ask me a question, how about the adhesion? Because in this case, in our earlier case, we were trying to build the structures from the substrate. But here it is something like from one substrate, we are trying to transfer the particle to the another region. So in order to take care of the adhesion, so what we are doing is we are just keeping a plate heating so that we try to we prepare the surface so that the particle gets adhered to it. So this is a kind of a Scotch tape test to confirm how the adhesion looks like. Okay, so we got a better adhesion, and most important thing is it is something like throwing a particle on a wall at a very high velocity. So what happens is the particle will easily get stick, and then the adhesion will also, there will not be any improvement in the adhesion. So this is some kind of preliminary result which we did. So now we will come to the exact 3D printing concept. So here in this case, as I had mentioned earlier, I need to have a film. So this film should have a sacrificial layer, and the material which needs to be 3D printed has to be coated. Okay, like in most of the 3D printing and additive manufacturing concept, our raw material will be either in the form of a wire, the form of a powder. Even people have attempted in going for sheets using a friction stir welding. People have made they have additive manufactured sheets. Okay, but in this case, this is a new concept where thin film is going to be your raw material. So now you have a flexibility to create any kind of thin film material. So like only thing is, for example, if I want to make nickel titanium, I can go for nickel titanium sputtering target or the thermal evaporation. I can coat it and then I can go for a 3D printing. Second concept is like I can go for multiple layers. Like one might be nickel, another might be titanium, and here this is a sacrificial layer, so that the transfer will happen with respect to these both on the surface. Third important concept is this is a kind of a maskless manufacturing, like how you go for a die-less manufacturing. So this is towards microelectronics printing, where people have to prepare mask. Here you don't require that mask. You can just directly give your drawing and you can do it. Okay, so this is a preliminary result which we did. So what we did is we had a small polyamide sheet. So we made our own XYZ stage, and this is a donor substrate and this is a donor film. Using an NDI, so using a thermal evaporation, we fabricated a small thin copper plate, copper sheet, and we tried to transfer the copper. Okay, so in fact, this is a kind of a deposition which we could observe. So this is a kind of nickel titanium copper where we could build some kind of structures or some kind of pillars out of these structures. Okay, so only thing is you need to move your acceptor, and then appropriately you need to instant the laser on the sacrificial and acceptor on the donor, and then from the donor the particle will move from donor to the acceptor, and it can build the structure. Either you can build a structure in this direction, or you can manipulate your base, or you can build a structure of whatever, you can build a 3D structure out of this. With this as an idea, so we thought of developing our own unit. So we did some theoretical analysis. In fact, the particle dynamics of the system, I will just show it over here. Okay, so this is the system which we have developed in our laboratory. So in this system, it's a complete closed loop system, which is kept inside a glove box, which has an automated donor and an acceptor film. So this donor film, so since we have a capability to go for a thin structures, we can go for a spin coating. We have gone for a spin coating, and using a spin coating, we have prepared our donor film. And then this donor film and the acceptor film are well interfaced with your laser system, so that even your micron displacement can be easily monitored. So we can go spot by spot. In fact, we have gone for a 99% overlap spot by spot, so that there will be a minute transfer which happens where we can have a proper features coming out of it. Okay, so as far as NITA structures is concerned, so this shape memory alloy has its own pseudo-elastic behavior. We were trying to fabricate some kind of strain gauges using these kind of shape memory alloy structures using this system. So when we try to fabricate, so there is a high-speed camera which is integrated, which will help us to understand the particle dynamics coming out of it, as well as it also helps us to understand the substrate through which the printing takes place. Okay, so this is a kind of printing. Here is a kind of a parametric optimization which we have done with respect to different laser fluents, where we are trying to build a track, a small micro track, and these are some kind of micro tracks with respect to different laser fluents and as well as with respect to different continuity. And this is a kind of large area printing where we were doing it to study the addition analysis of the system, and these are some kind of features which we have built. Okay, so this is a closer view of the feature where it's a nickel titanium based structure which we have built using these structures. In fact, we have fabricated some kind of strain gauges and using these NITA, which is showing a very good strain capability out of it. In fact, the interesting part of this, so this is how we have fabricated our strain gauge. So this is a strain gauge which is fabricated with NITA. So where there is a donor substrate and there is a sacrificial layer which is available, and we have deposited our NITA thin film using this one sputtering, and then the transfer was happening. So where we could fabricate, we want to map with the commercially available strain gauges. So commercially available strain gauges are available at different width. With a single shot, we can build up to 300 nanometer. So we have gone for 3-layer and 5-layer, and we have checked its performance. In fact, this is the performance of the strain gauge, what we have fabricated in-house, where with 5 layers, we could get up to 88 kilo ohm, and at 3 layers, we could get up to 220 kilo ohm. And we could easily achieve such kind of structures. Now, currently, we are also in the process of building some kind of micro gears. We are also in the process of developing some kind of piezoelectric and triboelectric based generators for some kind of application. Okay, so with this, I would like to close my lecture. So I thank my entire research group. So basically, this is a kind of a collective work which we have been doing for the last 10 years at IIT Indore, which is more focused towards additive. So apart from that, we work on device. Okay, so let me just show you a small video about our lab, and then we will wind off. Hope you could be able to see my screen. So these are some of the facilities which are available in my lab. So basically, we have different types of laser. So you name the laser, we have it. So we have a 2 kilowatt. Recently, we have a 2 kilowatt welding unit which is available, and we work on thin films basically for developing some kind of biomorph actuators, which I was mentioning. So we used to give samples to different colleges to educate them towards this shape memory alloy, basically towards developing a Make in India actuators. Okay, so our lab is a mechatronics and instrumentation lab. So we are involved in skill-based training with respect to pneumatic and hydraulic system. This is the wire arc additive manufacturing, which is developed in-house at IIT Indore. So these are some of the structures which we have fabricated. So it is completely dedicated for NITA. Currently we are focusing on towards aluminum-based components, but that is on a scale. So this system has a capability to fabricate 30 centimeter by 30 centimeter sphere. As I had mentioned in my presentation, so it has a capability to go for a substrate cooling as well as substrate heating. So we have designed a turret mechanism so that we can change the substrate heating as well as cooling unit. So we also work on NITA based welding, which is completely a tedious process, which is not possible by other techniques. So this is one of our student work, which he has fabricated NITA structures using friction stir welding. And this is an experimental test bed which we have developed at our lab with a laser displacement sensor to study the actuation behavior. So basically, this is an electrical actuation which is being performed to study the reliability and the life cycle of the structures what we have fabricated. So this is the laser actuation of the NITA structures. So this is a concept called die-less manufacturing. So where we are involved in some kind of laser forming of brake pedals and clutch pedals, which is for some, as a consultancy, we work with different industries in making prototyping brake pedals and clutch pedals using laser forming. So this is one thing which we were employed in making engine cabinets using laser forming. So this is a kind of a laser peening which we were involved. So this is an SMA integrated composite structure. So which we are closely working with DRDO to making some kind of missile flappers. So this project is almost over. So and we have submitted the components to them for testing. So this is a kind of SMA based perpetual machine. Basically, it's a kind of SMA based heat engine, which it is mainly used for harvesting the energy from hot water condition. In fact, as an extension of this work, we have worked with one industry to make an intelligent cooling fans out of it, smart cooling fans out of it. So this is called as an SMA bimorph. So you don't require any kind of training for programming these materials. So whatever displacement you require, or whatever frequency you require. So based on that, during the deposition itself, we can program it so that it can actuate it with respect to that frequency. So it has a potential application as intelligent mirrors for astronomical telescopes. And it also has a potential application towards soft robotics. And we are also developing some kind of PDMS based soft robotics for high frequency applications. So we have so this bimorph is completely unique of its kind. On an international context, we are the first to fabricate an 1 meter by 1 meter area. So we are promoting this technology so that more faculties can use this for different applications. This is an SMA actuated jellyfish, so which in collaboration with one of the DRDO we have developed. So these are some kind of underwater robotic systems which we have developed with a shape memory alloy structure, which is a completely in-house developed technology. So currently we are moving towards these lead-free piezoelectric smart actuators. So basically the idea of these lead-free piezoelectric actuators is to harvest the energy. So wherever you have vibrations, we can harvest the energy, or wherever we can apply a load, we can harvest the energy. So here, this is one of our research scholar, Dr. Rajagopalan, who's now working in Germany. So he has fabricated piezoelectric structures through zinc oxide, and by just applying a load on it, or so he is trying to generate the energy, and that energy is used for a chemical reaction. So some kind of burglar alarm also, self-energized burglar alarm also we have developed. And one interesting area which currently we are focusing is to harvest energy from the flapping structures. Like we can integrate these piezoelectric structures in a kind of flag. So as the flag flaps, we can harvest the energy. So this is a wind tunnel experiment where we have developed a flag kind of arrangement, and then we are harvesting energy, which you can see it at the back. Now we are more focusing towards triboelectric nanogenerators, lead-free triboelectric nanogenerators, which has a capability to harvest energy from machine tool vibration. And it can be used for condition monitoring also. So this is a compressor in which a TENG is kept, and then we are trying to harvest the energy from the vibration. So with this, I would like to close my lecture. So if there is any questions or queries, I would be happy to address it.
Yeah, thank you, Dr. Palani, for a very wonderful talk, which is very enlightened and I would say very rich talk, very informative content. I believe the all audience would have definitely benefited out of your talk. So you covered entirely from macro structure to micro structure. Even you went down to nanostructure, component making using the laser assisted processes. So with this, I request audience to ask questions if you have any. So to audience, Dr. Palani is also very open to help students community. So you can actually, he's very student friendly. You can approach him if you have any interest pursuing your research or Dr. Palani, I'm taking advantage of your this thing, knowing your nature. Yes, so you can approach Dr. Palani for any academic related help.
So actually, so I take this forum as an opportunity. Like our main motto of this lab is to focus on shape memory alloys. So more people should work on shape memory alloys, because that field almost due to the limitation in the material, it got stagnated. So now a few communities